These are the section 2.2 notes, graphs of relations and functions. So we're going to start off with looking at the different parent functions. Parent functions are just the original version of a graph with no shifts. It hasn't moved up or down vertically, left or right horizontally. It hasn't been stretched so that it's skinnier or compressed so that it's wider. Hasn't been reflected over the x-axis or the y-axis or anything. So our parent functions are absolute value, quadratic, square root, cubic functions, cube root functions. Later on we'll learn about rational functions, logarithmic functions, etc. So what we're going to do with these parent functions is we're going to start with the graph that I have graphed for you and a table of values that I've given you, and then we're just going to shift the graph a little bit and make sure that we can create our own table of values and still graph the function and find the domain and range. So here we have the absolute value of x plus 2, and when we plug values into the absolute value of x, we know that absolute value symbols, that those vertical lines, they just take whatever number is inside and they force it to become positive. So the absolute value of -2 is positive 2, plus 2 is 4. The absolute value of -1 is positive 1, plus 2 is 3. Absolute value of 0 is still just 0, plus 2 is 2. And what we can see is that from the original table, each of the y-coordinates is just increasing by 2. So 3 and 4. And then I'll go ahead and graph. For the domain, those are the x values that I'm able to plug into the equation. I can still plug in any x value and force it to become positive, so any negative is fine, any decimal, any positive. You can see that on the graph, because all of the values exist on the graph from left to right, we can see all the numbers there. The range here, you can see that the very lowest output is a 2, and then all of the other outputs of the function are above 2. So I'm going to say my range starts at 2 and then is all the numbers that are greater than that, so from 2 to infinity. Right, next we have a quadratic. So we're going to take the values, we're going to square them, multiply them by themselves, and then force them to become negative. So -2 squared is positive 4, and then the negative version of positive 4 is -4. -1 squared is positive 1, the negative version of that is -1. 0 squared is just 0. The negative version of that is -0, which is still just 0. So we can see that what's happening is we're taking this table and all of the y-coordinates are just multiplying by -1, or they're becoming the opposite sign. So -2, -4, -1, -1, 0, 0, 1, -1, 2, -4. There's our quadratic. For the domain, you can still plug in any number, multiply it by itself, force it to be negative. For the range, we can see that we're going to have all these negative values, which makes sense. We're taking something that's always positive and we're forcing it to be negative. So we have all these negative values for outputs, and then 0 is an output, but no positive numbers can be outputs. So we have negative infinity up to 0 for the range. For the next function, we have a square root function, and you'll notice in the table that instead of doing a table of values from -2 to +2, I chose values that made more sense for a square root graph. So I didn't use any negatives because you can't square root a negative and get a number that you can graph. You can only get imaginary numbers from that. And then I also chose perfect squares to plug in so that I would be graphing numbers that are easy to do as opposed to decimals. So square root of 0, square root of 1, square root of 4, square root of 9, square root of 16. Those are the numbers I chose. Over here, we're doing x minus 3 underneath the square root. So when I chose my table, I was thinking, well, some number minus 3, it would be helpful if that equaled 0, so I'd be taking the square root of 0. Some number minus 3 will be helpful if that equaled 1, so I could be taking the square root of 1. So that's what I was thinking as I did each of these numbers, was what did I want to end up square rooting. So if I plug in 3, 3 minus 3 is the square root of 0. Square root of 0 is 0. 4 minus 3 means we're square rooting 1, which is just 1. 7 minus 3 means that we're square rooting 4, which is 2. 12 minus 3 means we have 9. Square root of 9 is 3. And then 19 minus 3 is 16. Square root of 16 is 4. And here we're not doing plus minus with our square root because this is just a positive square root sign. So we're just getting the positive answer. So I have 3, 0, 4, 1, and 7, 2 would be over here. I'm just going to graph it, even though it's off the graph, just so I can see a little bit more. So it looks like this. All right, so for our domain, I can't plug in any values in less than 3, because like if I was to plug in 2, 2 minus 3 is a negative, and that's not going to give me a real output, and the domain is based off of what outputs are real. So to start with, I can plug in 3 and anything larger than that. So my domain is going to be 3 to infinity. And then as far as my outputs go, since I'm taking the positive version of a square root, I can get 0 at the smallest number. You can see that. Here's a y coordinate or an output of 0. And then I can get positive outputs, but I'm not going to get any negatives because I'm not taking the negative version of the square root. So my range is from 0 to infinity. All right, next we have cubic graphs. We're taking the x-coordinate and cubing it. So this is saying take the x-coordinate, cube it. So -2 times -2 times -2 is -8, and then cut it in half. So that'd be -4. -1 cubed is -1. Cut it in half, we get -1/2. 0 cubed, 0 multiplied by 1/2. So you can see that what we're doing is taking all these y coordinates and we're cutting them in half. Okay, so -2, -4, -1, -1/2, 0, 0, 1, 1/2, and 2, 4. Okay, so here for our domain we have -infinity to positive infinity. You can always take a number and multiply it by itself 3 times. For our outputs, we have all the negative numbers, all the positive numbers. All right, let's try cube roots next. So here, this is similar to what I did with the square roots. I was thinking what numbers are easy to cube root. So 8 and -8 are easy to cube root. 1 and -1 are easy to cube root, and 0 is easy to cube root. And so those are the numbers that I used. So over here, I was thinking if I have x plus 2, what number could I add to 2 to become a number that's easy to cube root? So -10 plus 2 is -8. The cube root of -8 is -2. Next, if we plug in -3, we have -3 plus 2 is -1. The cube root of -1 is -1. So you can see that what we've done is in this table, if you compare this table to this table, all the x coordinates are just 2 less. They've just subtracted 2 to account for the fact that we're going to be adding 2 and then getting a number that we can cube root. So -2 plus 2, the cube root of 0 is 0. -1 plus 2 is 1, the cube root of 1 is 1. 6 plus 2 is 8, the cube root of 8 is 2. So I can't graph that first one, but -3 minus 1, -2, 0, -1, 1, and 6, 2, I'm going to go ahead and do that one. All right, and here for the domain, you can cube root any number, negatives, positives, it just might not be a nice whole number. The range, your outputs, you can have negatives, you can have positives, all the numbers there. All right, so next I want to talk about graphing piecewise functions. A piecewise function is a function for which various equations are used for various intervals of the domain. Doesn't make a lot of sense now, but it will in a second. The simplest example of a piecewise function is the parent function for an absolute value equation. So if we look at an absolute value equation, we can cover up one side of it at a time and see that each piece looks like a line, a straight line, a linear equation. So this would be a straight line with a negative slope that crosses through a y-intercept of 0. And you can't see it very well on here because this graph doesn't have a grid, but the negative slope would be down 1, right 1, down 1, right 1, down 1, right 1. So for this portion of the graph, I could write that the equation of the line is y equals negative 1 over 1 x plus 0. So slope of negative 1, y-intercept of 0. If I cover up the other side, then over here we still have a straight line. It still has a slope of 1, but this time it's a slope of positive 1, and it still has a y-intercept of 0. So for this other portion, I could say y equals 1 over 1 x plus 0. So you can see that we have various equations. We have two equations. We have one equation for all the x values that are less than 0, and one equation for all the x values that are greater than 0. And that's what they mean by various intervals. We have two intervals, less than 0 and greater than 0. So the way that you would write this piecewise function is you would say that y equals, and then you do a squiggly bracket, and we would say negative 1 over 1 x plus 0 if x is less than 0, if we're looking at the left piece. Positive 1 over 1 x plus 0 if x is greater than 0, if we're looking at the right piece. Now, we have to include this point in the middle. It's not a hole. It's not missing from the graph. So for one of these, and it doesn't matter which one, you just put an equal to make sure we have that point in the middle. Now, most people would not put the plus 0 on the end. They would not put negative 1 over 1 in the front. So to write an absolute value equation, you would write negative x if x is less than or equal to 0, positive x if x is greater than 0. So to graph an absolute value equation, you can graph y equals the absolute value of x, or you can graph an equivalent piecewise equation using a straight line on the left half, a straight line on the right half. And that's how piecewise functions work. So what we're going to do next is we're going to graph a couple piecewise functions. So this first one says f of x, or y equals 1 if x is less than 2. Well, the graph y equals 1 just means that all the y coordinates of all the points are 1. So it would be this horizontal line right here, y equals 1. So I'm going to start by graphing that. I'm graphing in pencil because I'm about to erase part of it. So after that it says take the x values that are less than 2. So 2 is the point where we're dividing the graph between left and right. For the piecewise example, we divided it at 0, but here we're dividing it at 2. It says choose all the values to the left of 2. So this is the part of the graph that we're using. We're going to keep this, and we're going to get rid of this part. Okay. Next it says graph f of x equals negative 1, which is y equals negative 1. Again, we're splitting the graph in half at 2. Choose all the numbers greater than 2, which is to the right of 2. It also says that you can equal to, which means I'm going to fill this in right here. You can equal to. And then everything to the left of 2 I'm going to get rid of. And there is that piecewise function. For this one, if we looked at the domain, what x values can you plug in? You can plug in all the negative x values here, negative infinity, negative 100, negative whatever. You can plug in 0 here, and you can plug in anything that's less than 2. For this one, you can plug in 2 exactly, and then any numbers bigger than 2. So for the domain, we would say negative infinity to infinity. You can plug in any value for x, you just have to choose if you're doing it for the left piece or the right piece. As far as the outputs go, the y coordinates, you only have 2 options. Your output is either going to be -1 or it's going to be +1. It's not going to be anything else. So for this, we're going to say it's a set of numbers. So I've got a squiggly bracket, -1, +1, and those are the only numbers in the set. All right. Let's graph this next one. This next one says to graph a quadratic function and to subtract 4. So what I'm going to do is I'm going to take my quadratic function and we're plugging in these x coordinates and getting our outputs. But then once we have the outputs, it says that we're going to subtract 4 from it. So -2 to +2 for the x. And then subtract 4. So -2 squared is 4, minus 4 is 0. -1 squared is 1, minus 4 is -3. 0 squared is 0, minus 4 is -4. So you can see that what we've done is we're taking each of these y coordinates and subtracting 4. 0, -3, -4, -3, 0. Okay, so I can go ahead and graph that. And for the piecewise function, it says we're actually using not everything to the left of 2 and to the right of 2. We are doing that, but we're kind of doing a sandwich here between -2 and +2. So think about -2, think about +2, keep everything in between, keep the sandwich that's in between, the numbers that are between those, and then get rid of everything else. So I'm just going to erase the rest of it. Okay, and then here we have a linear equation. 1 is the number in front of x, so that's a slope of 1, and then a y-intercept of -2. So here's -2, up 1 over 1, up 1 over 1, up 1 over 1. So here's our linear equation. Okay, now it says look at the 2, and keep all of the numbers that are greater than 2, so everything to the right of 2. So look at 2, keep everything to the right of 2. Now normally, since this doesn't have an equal to, on the straight line, I would draw a circle here and I would not fill it in, normally. However, these two graphs are coming together, the quadratic and the straight line, and in the quadratic, that point was filled in because for the -2 and the +2, it said equal to and equal to. So this was filled in and filled in. So if you have a circle that should not be filled in, and a circle that should be filled in, and they're meeting at the same point, then you just fill it in. Okay, so I kept the right side. I'm going to erase the left side. Okay, and then for the domain, I have to think about the x values that I can plug in or look at the x values that are represented on the graph. Both of those are the same answer. So the lowest x value I can see is -2. And then all these x values are represented and the x values go to the right forever. So -2 is the smallest x value that we can plug in, and then we can plug in any x value that's larger than that. For the y coordinates, the very lowest output that we have, or the smallest y coordinate that we have, is -4. And then all the y coordinates that are bigger, these other negatives are included, 0 is included, and then all the positives are going to be included. So -4 is the smallest y coordinate, but then everything else from there up will be included. All right, next we're going to learn about a characteristic of functions. One of the characteristics we've already learned is domain and range. Another characteristic we're going to learn about functions is increasing, decreasing, and constant intervals. So increasing and decreasing are more common. Constant you see in piecewise functions, but otherwise not as much. This is just describing kind of the slant of the graph when you look at it visually, or taking the table and describing if the y values are going up, going down, or staying the same. So here is an example of an increasing function. And I always think of these functions as having a little stick figure on them, and this little stick figure would be walking uphill. That's how I can tell that it's increasing, because I'm reading the graph from left to right. If I look at the table, I can tell that it's increasing because as we look at the table from left to right, as we look at x values that are getting bigger, the y values are getting bigger. So I can see that these y values are increasing from left to right. Here, if I put a stick figure on this negative linear function, the stick figure would be walking downhill. So this is a decreasing function. And if you look at your y coordinates, you can see that your y coordinates are getting smaller. So they are decreasing in value. They are getting smaller. Here we have just a horizontal line. So if we had a stick figure walking here, this would be a very easy walk because it's constant. No uphill, no downhill, just stays flat. And you can see what that would look like in a table. The y coordinate would just stay the same every time. So this would be, as you look from left to right, this would be constant. All right, so for these next couple examples, it says identify any intervals on which the function is increasing, decreasing, or constant. So I'm just going to take my stick figure and walk the stick figure uphill, downhill, or constant. And then the intervals are going to be the x coordinates that make that happen. So the x coordinate of a left arrow is -infinity. So right now my stick figure is walking uphill, so my stick figure is increasing. My stick figure increases to the very top. Right up here, this is an x coordinate of 0. Be careful not to put 4, that's the y coordinate. This is an x coordinate of 0. And then after the stick figure passes the top here, then the stick figure is going downhill, which is decreasing and decreasing to a right arrow, which is an infinity. So for this, we would say the increasing interval is, and we would write the numbers that the word increasing was in between. So the increasing interval is from -infinity to 0. The decreasing interval is from 0 to infinity. All right, over here, we have a piecewise function that was graphed. It actually has 3 pieces this time. And we have this horizontal piece. So if we start our stick figure walking, the stick figure is going to start walking at this arrow, so that's a -infinity. And this is constant. The first piece is constant. And it's flat until you reach an x value of -3. And then the stick figure starts walking uphill a little bit. And it's uphill until you reach a x value of 1. And then it flattens out again. and then it's constant. And it's constant all the way to the right arrow, which would be infinity. So here we would say for increasing, I'm going to do 3 this time. A lot of times when you're asked about this, they just say increasing or decreasing. In this case, we're adding constant because it's a piecewise function, and sometimes we have those flat pieces. So for the increasing interval, the word increasing is in between -3 and 1. There are no decreasing intervals. And the constant interval is -infinity to -3 and 1 to infinity. And make sure anytime you have two answers like this, put a U in between. It shows that you need both of the answers to be right. Whenever we do increasing and decreasing intervals, if we include the infinities, we still always use parentheses because those are not values that we can include. You're never going to get to the arrow. You're just going to keep tracking that way. Okay, now what we're going to do is we're going to go back to some of these, and we're going to find the increasing and decreasing intervals for the rest of these. So here, -infinity, +infinity, my stick figure is walking downhill and reaching an x coordinate of 0 and then walking uphill. So the increasing interval would be 0 to infinity. The decreasing interval would be -infinity to 0. If we were to think of this one the same way, the answer, even though you've shifted the graph up and down, it doesn't make a difference because you're starting at a -infinity, you're ending at +infinity, and the stick figure switches directions at 0, just like they did on the previous graph. So the increasing and decreasing intervals are actually the same, even though the graph has moved up. All right, here, now this graph, even though it's a U-shaped graph, it might as well be the previous graphs because we're still starting at -infinity, ending at +infinity. We're still going downhill first and then going uphill second, and we're still switching directions at 0. So the increasing and decreasing intervals are the same here as they were for the last two graphs. But when we look at the next graph, things are going to be a little bit different because the graph has flipped upside down. And so if we were to consider the stick figure here, they would be walking uphill first. They would reach the x value of 0, and then they would walk downhill. And the left arrow is -infinity, right arrow is +infinity. So notice it doesn't matter if my arrows are pointing up or down. I don't care if they're pointing up or down. I care that this is my left arrow, so it's -infinity. This is my right arrow, so it's +infinity. So my increasing interval this time is -infinity to 0, 0 to infinity. All right, here, so I've got a stick figure, starts at 0, goes to the arrow, and only walks uphill. So this is 0 to infinity, and for decreasing, I'm going to say none. This graph is very similar. If we have our stick figure, they are only walking uphill, they are only increasing, but they're not starting at 0 this time. They're starting at an x value of 3. So this would be increasing from 3 to infinity. Decreasing would be none. Okay, very close to being finished. So here we have our cubic function So here is our stick figure, negative infinity, positive infinity. So this stick figure, it's kind of like they're climbing up a cliff. They get to a little ledge in the cliff and then they keep climbing the cliff. So this is increasing, increasing. They took a little rest in the middle. But we would say this is increasing from negative infinity to positive infinity. They never switched and went downhill. They never started decreasing. So increasing the whole time, decreasing none. You can see that that's the same for this graph as well. This one would be like they were hiking, walking uphill, and then they had to like climb up and over a boulder, and then they kept climbing uphill. So this one, again, is increasing and increasing with a very steep increase right in the middle. Again, same thing on this graph.